So I've got this petition. Just need a signature before I turn it into the department. You need it? This oh 430. Oh, okay. Yeah. I thought for this class, I'm like, this is already a graduate class. I don't know if you're also considered my advisor. I mean, technically I am, but I think for what's it called, for ethical purposes, you should probably get Dr. Weiss assigned the next one. Gotcha. Yeah.
Her class is right after us, so.
Oh yeah, she's coming right here. So yeah, just wait right after. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good to hear. All right, it's week two. Yeah, week two. So yeah, start a brand new week. Still early in the semester, so yeah, still going. Okay, all right. So today we're gonna first thing we're gonna do today is we're gonna finish up our lecture notes. So we started our lecture notes on kind of just the introduction to the direct stiffness method. So I have one more example involving springs, where I think you'll kind of see the whole kind of finite element process. And so I think it'll be good to kind of, because the last time we went over it, we kind of went really slow talking about every step. But I think once you see a problem, start to finish, every step done, I think that'll help kind of visualize the whole thing. And then after that, we're going to start our lecture notes on truss elements. And so, the thing with the direct stiffness method is that, we kind of have to derive each type of element very explicitly. And so we're going to go through different kind of structural members, springs, trusses, beams, and then eventually frame elements as well. Okay. All right. So, another announcement. Homework one has been posted. So that is the first problem set. It is a little bit lengthy. Basically, it's going to get us through trusses and springs. So the due date for that is going to be February 8th, which is going to be a Sunday. So that's not this Sunday. It's going to be next Sunday. Okay. Normally, I have homeworks due on a Friday, but I know for grad students, I know it's weekends is just I think better for I think a lot of you guys to work, so that's why I have it due on Sunday, 11:59 p.m. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So we were in the middle of going over the direct stiffness method. All right, so the direct stiffness method is kind of our first exposure to the finite element process or the finite element method. Okay, so remember the direct stiffness is a very specific implementation of the finite element process. Okay, and like I said last time, that the direct stiffness method on its own is not particularly useful in the sense that it's not really used to analyze real structures. And so the whole point of this section of the class is just to kind of illustrate to you, what are the main steps to perform a finite element analysis. Okay. Right. Because no matter if you're using the direct stiffness method or you're using isoparametric elements, the general steps are the same. It's just the details of each step and kind of how each step is implemented is a bit different. So the first step to a general FEA is to basically compute the element stiffness matrices for every element. Okay. So every element in your system, every element in your mesh, every single one of those is going to have an individual element stiffness matrix, and so you need to compute all of them. Okay. Step two is that once you have all of the individual element stiffness matrices, you need to assemble them together into a single global linear system. Okay. All right. Step three is to apply boundary conditions. Because once you have your global linear system, you won't be able to solve it at that point because it's, well, first of all, there's still unknowns in that linear system, but also it is, basically it's going to be a symmetric matrix, so you can't solve it. So you need to apply boundary conditions in order to make it solvable. Okay. And then step four is to solve. Okay. And so this step typically is done by computer because, normally you don't want to be solving these massive linear systems by hand. So for this class, typically we're going to use MATLAB. And so at the end of the example, or at the end of this first example today, I'll kind of show you how I kind of set this up in MATLAB and solve. But you can use any tool that you want. So I know that there are websites for solving linear systems. You can just plug that in there. If you're good with Python, then that's a possibility too. So just you have to solve it with computers somehow. Okay. But we will be using MATLAB for this class. Okay. And then technically after step 4, there is a step 5 for post-processing, but at least now, when we're going over the theory, we're not going to worry about that too much. We're going to stop at the solutions. Okay. Okay. All right. So that is a summary of the finite element process. So let's go ahead and apply this to another example and kind of see how this is applied. Okay. Okay. So let's consider the following system that has 3 springs to it. Okay. All right. And so let's say we have our fixed wall here. Okay. We're going to have 1 spring attached to the wall, just like that. Okay, we'll call this spring A. And that's also going to be our element A as well. Okay. So this spring A is going to have its own spring constant. So we'll call it Ka. Okay. This Ka is going to be attached to a wooden block. Okay. So the block is not going to be an element. It's just a way for us to connect these springs together. Because to this block, we're going to connect 2 other springs in parallel. Okay. So you're going to have 1 spring up top. This is going to be our element B. Let's spring constant KB, okay? And then on the bottom here, we're gonna have another spring. We'll say element C, and it's gonna have its own spring constant KC as well, okay? Okay. All right, and so another thing we need here is we need our loads, and so we need to apply our forces. And so we're gonna have a force that's being applied on the top here. So we'll say we'll have a tensile force, we'll call that F3, okay? And then on the bottom spring here, we're going to have a compressive force. We'll say this is F4. Okay. Okay. All right, so another thing we're going to do here is we're going to label all of the nodes in the system. So basically everywhere where these systems connect. So we're going to say that the node attached to the wall, we'll call that node 1. Okay. Node number 2 is going to be where all these springs converge. And so the entirety of the wooden block is going to be node number 2. Okay. And then we need nodes for the 2 endpoints too. So we're going to say the top endpoint is going to be node 3. And then the bottom endpoint here is going to be node 4. Okay. All right. So unlike the previous problem, for this problem, we are going to actually use some numbers here. So we're going to actually be able to compute a solution. Okay. So let's go ahead and list out those values. So the parameters of our problem here, we need values for all 3 spring constants. So Ka, Kb, Kc. So Ka is going to have a spring constant of 500 newtons per meter. Okay. Kb is going to have a spring constant of 100 newtons per meter. And then Kc is going to have a spring constant of 250 newtons per meter. Okay. Now these are very low spring constants, and so these are basically all just slinkies. But I try to keep the numbers low, just to kind of make the numbers a little bit more easier to work with for this problem. Okay, and then we need numbers for our 2 forces too. So F3, the tensile force we'll say is going to be 100 newtons. Okay, and then F4, which is our compressive force, we'll say is 50 newtons. Okay. All right. And so for this problem here, what we're looking for is we want to solve for the displacement of all of the nodes in the system. So node 1, node 2, node 3, node 4, we're going to compute the displacement for all of those. And the way we're going to do that is through the finite element. Okay. All right. All right, so a lot going on in this problem, especially compared to our last example. So are there any questions on just the setup for this example? Okay, all right, so let's go ahead and start solving it. And so in order to solve this problem, we need to apply our finite element method. And so basically this 4-step process here we're going to apply to this problem. Okay. So I will warn you guys right now, for the next, I would say 4 to 5 weeks, it is going to feel very repetitive because every single problem that we're going to do is going to follow the same 4 steps. And so it's going to be element stiffness matrix, assembly, boundary conditions, solution. And so there's going to be a little bit of wrinkles. And so, we're going to be looking at different types of elements. We're going to do a little bit on the post-processing. We'll learn how to compute stresses, but it's going to be the exact same process. And unfortunately, with FEA, these are not the most exciting problems to do. You're talking about writing just a bunch of matrices over and over and over again. So I know it does get repetitive. And I was telling someone before the class that unfortunately there is no shortcut. There is no kind of easier or more efficient way to do it. You just have to write all of the matrices, and you just have to kind of be meticulous with it, because the thing is with these problems that, if you do kind of skip steps, you do kind of try to, make your time more efficient, I guess you can say. That's when you start to make mistakes. And unfortunately, with these large linear systems, that a small mistake can, result in actually a big error in the solution. So, you might get a solution where you think you're really far off, where in reality, you just kind of made one little mistake in the process. So, you kind of have to just be really meticulous through this whole thing. Okay. Okay, so let's go ahead and start. So first step is we need to write out our element stiffness matrices for all of the elements. But the tedium is kind of on purpose, and there's a reason why FEA is traditionally done in a computer, because these you'll see very quickly that it starts to get out of hand if you try to do hand calculations for a more complex problem. Okay. Okay, so we have 3 elements in this problem. So we have element A, our first spring, element B, our second spring, and element C, which is our third spring. Okay, so let's go one by one. Okay. So element A, its element stiffness matrix looks like the following. So you have F1, F2 is equal to Ka minus Ka minus Ka, Ka, okay, multiplied by D1, D2. Okay. Remember, for these element stiffness matrices, it's not only important to basically write out the numerical values of the matrix itself. You also need to specify which nodes this element is connected to. Okay? And so by this matrix here, we can see that we basically indicated that element A is connected to nodes 1 and 2. Okay. And so if we go back to the problem figure, we can see that that is actually true. So element A, this one right here, right? On the left-hand side, this element is connected to node 1. On the right-hand side, this is connected to node 2. Node 2 being that kind of big block that's connecting all the springs. Okay. Okay. So let's go ahead and fill in the values, just because we do have the values for Ka actually. And so we fill in the values for this. We get F1, F2 is equal to Ka is 500 newtons per meter. So this is 500 minus 500 minus 500, 500. Okay. D1, D2. Okay, good. All right, so let's repeat the same thing for element B. Okay, so element B, if we go back to our problem figure, we can see that element B on the left-hand side is connected to node 2, so that is the wooden block. And on the right-hand side, we have the free node, which is where the force is being applied. That is node number 3, okay? So element B here, we're going to have F2, F3, okay, is equal to. Then we have the spring constants for element B. So spring constants for element B, if we look back up here, is 100 newtons per meter. So let's go ahead and fill that in. It's going to be 100 minus 100 minus 100, 100. Okay. Multiplied by D2, D3. Okay. Which again, you know, what we're indicating is that this is connected to nodes 2 and 3. All right, and then finally we have element C. Okay. All right, so if we go back to our problem figure, we look at element C, right? So this will be kind of the first interesting element that we look at because, you know, for the first time, we have nodes that are not consecutive to each other. Because on the left-hand side, element C here is connected to node number 2. And on the right-hand side, this element is connected to node 4, okay? So our element stiffness matrix has to reflect this. And so we have F2, F4 is equal to spring constant for element C. What was that? That was 250, okay? So this is 250 minus 250 minus 250, 250. Okay. D2, D4. This is nodes 2 and 4. Okay. Okay. So those are our 3 element stiffness matrices for this problem. So, you know, so far, still pretty reasonable. So, but that does it for that step. Okay. Any questions on this so far? Yes.
Yeah, my math is a little wonky. So when I'm thinking about it conceptually and stuff like that, basically it's saying that and typically on the left side we'll have our forces, right?
Yeah.
And on the right side we'll have like the our parameters, I guess.
Mhm.
So like stiffness and then the nodes and then why is it like I kind of like forgot like what like the like a lot of my matrices kind of math stuff, but basically you have the same number and it's kind of like repeated where it's like negative and positive.
Mhm.
What exactly is that?
Yeah. So that's reflecting the fact where you know that basically shows kind of the relationship between force and displacement for the spring, right? So so last time, you know, we basically took Hooke's law for a spring. So if you have kind of a spring like this, right? And if you apply a force to it,
Yes, yeah.
and the spring is going to be elongated by D, right? Right. And so our typical Hooke's law is basically says that the force that you apply on the spring is equal to K times the displacement, right? So that's kind of the typical Hooke's law. What we did last time is we kind of generalized this where we said that, you know, if you don't have a wall here, oops, right? So you basically have, you know, a free spring where each side of the spring kind of individually kind of deform, right? And what we did is we kind of generalized this equation here. So that's essentially how you get these negatives here, where if you kind of multiply this through, right? So basically, you know, we're going to get basically two linear equations from this. So you basically multiply this first row by this column, and that's going to equal that. So you have F1 is equal to Ka times D1 minus Ka times D2. Yeah. So that's kind of it's just a generalization of Hooke's law. And so we have kind of those two equations, because then the other side, the other equation is F2. We form the same thing. We multiply this row by this column. We get minus Ka times D1 plus Ka D2. Yeah, so it's just a generalization of that. And so that'll be a trend. And so, you know, you'll see when we get to trusses, we're going to do kind of the exact same thing. Yeah. Mm-hmm. All right, any other questions on this step here? Okay, all right, so let's go ahead and move on to the next step, right? So now that we have all of our element stiffness matrices, the next step here is going to be assembly. So we need to assemble all of these element stiffness matrices into one global system. Okay, because basically, you know, we want a single system of equations that we can use to solve for our three nodal displacements, D1, D2, D3, D4. Okay, because you can see that they all show up here, right? So D1 through D4 are part of our element stiffness matrices, but they're all in separate systems. And so in order to actually properly solve this, they all need to be in one. Okay, so in this particular case, we have four nodes or 4 degrees of freedom. So our global linear system is going to have 4 rows and 4 columns. Okay, so first let's write out the forcing vectors. So we have F1, F2, F3, F4. Okay. And then we have the matrix. So our matrix similarly is going to have 4 rows. And so we write them out. We have D1, D2, D3, D4. Okay. Another thing that I'll do just to kind of help us out with the assembly is I'm going to write out the columns as well, because each column also corresponds to each degree of freedom as well. So first column is going to be D1. Second column will be D2. Third column will be D3. And then fourth column will be D4. Okay. Okay. Now to assemble this matrix, we're basically going to take all of our element stiffness matrices that we computed in part 1, and then basically just kind of insert them into the proper location into our global linear system. Okay. Okay. And where we insert it depends on which nodes that element corresponds to. Okay. So let's start with element A. Okay. So element A, we know is working on nodes 1 and 2. Okay. So we're basically going to go to our global linear system and look for the rows and columns associated with nodes 1 and 2. Okay. And so if we kind of, you know, partition that out, you can see that D1 and D2 are the first 2 rows and the first 2 columns. So we're basically going to see where those two intersect. Okay. Okay. And so those two are going to intersect in that kind of upper left quadrant right there. Okay. All right, and so now that we've kind of partitioned that area out, let's go ahead and write in the values for element A. Okay, so element A, we know we have 500, minus 500, minus 500, 500. So we put that in here. 500, minus 500, minus 500, and 500. I'm going to leave a little bit extra space on the bottom right one just because we're going to add stuff to that. Okay. Okay. So that's element A. since I'm working with an iPad right now, I have the benefit of using different colors, but if you're working on a pencil and paper, I don't know, bring different color pens next time, I guess. But element B, okay, we know from earlier that element B is acting on nodes 2 and 3, okay? So just like we did with element A, we're going to partition out the area in our global linear system that corresponds to nodes 2 and 3, okay? So that's going to be the second row, second column, and third row and third column, okay? And so if we kind of box that out, that's basically going to be this region right here. Okay. All right, so let's go ahead and insert the values into there. So we're basically just going to take the values that we computed up here and put it down here, okay? Remember, whenever you have overlapping areas in your matrix, you're basically just going to add those numbers together. Okay, and so this first one here, we're going to have 500 plus the 100 that comes from element B. Okay, and we're going to fill in the 100 newtons per meter on all the other spots on that matrix. Okay. All right, and then finally we come to the interesting one, which is element C. Okay. So element C is the interesting one because this is the first time that we're going to have nodes that are not kind of consecutive to each other. And so the way that we actually insert this into the global linear system is also going to reflect that fact as well. Okay, so element C is connected to nodes 2 and 4. Okay, so that means the way where we insert this is going to be the second row, the fourth row, and then the second column and the fourth column. Okay. Now, what does that look like? Now, the second row and fourth row are not next to each other, right? And so we can't just draw one big block, but we can separate them. And so it's going to look like this. And I'm going to use solid lines just to make it a bit more clear. All right, so the first place that we're going to insert is going to be the second row, second column, which is that spot right there. Okay. Next, we have the second row and the fourth column, which is that spot right there, right? So they don't have to connect, right? And so, in fact, a lot of the cases we'll see later, we're going to have cases where they don't connect to each other. Okay. Next, we have the fourth row and the second column, which is that spot right there. Okay. And then finally, we have the fourth row and fourth column, which is that bottom right spot right there. Okay. Now, besides the fact that we have to separate these two, they're not all in one contiguous block, it doesn't change anything else. And so all the values that we insert are still going to be the same, okay? So on the top left part right there, we're going to insert a positive 250. So we're going to add 250 to those two there, okay? Okay. On the top right corner, bottom left corner, we're going to insert a minus 250. And on the bottom right, we're going to have a positive 250 on that one. Okay. Yes, question? Yeah, so the 250 comes from our element stiffness matrix for element C, which is what we computed earlier. So each element stiffness matrix reflects a spring constant for that particular element. So since element C has a spring constant of 250, that's what we insert when we go insert elements. Yeah. Make sense? All right, and then of course, whatever areas that we haven't boxed that don't have a value yet, we're just going to put a 0 there. Okay? So we're going to have zeros here, just like that. Okay. So the way I did this problem is that, I kind of filled in the values for those constants right away. Another way that you can do this, and and honestly, I kind of prefer this way, is to wait until the end to kind of plug everything in. So, usually in that sense, it's a bit easier to kind of see where they come from. And so, for instance, instead of plugging in the value of 500 for Ka, we can kind of just leave this as variables, right? And so we can basically say that this is going to be a positive Ka, minus Ka, minus Ka, positive Ka, okay? Or if you feel comfortable plugging in from the beginning, you can go ahead and plug that in as well, okay? That way you can kind of just do all the plugging in at the end, and then, you can kind of avoid some arithmetic mistakes, or at least cut down, okay? All right. All right, so now that we've inserted all of the element stiffness matrices, let's go ahead and simplify this. And so, we have some arithmetic to do, okay? And so if we simplify that, we get the following matrix. So we have F1, F2, F3, F4 is equal to, we have 500, minus 500, 0, and 0, okay? Minus 500. Now, next we have the sum of all three of those terms. We have 500 plus 100 plus 250, so that is 850. Okay. Then we have minus 100 from KB, and then minus 250 from KC. Okay. Third row, we have a 0, minus 100, positive 100, and then 0. Okay. And then fourth row, we have 0, minus 250. That comes from element C, 0, and then positive 250. That comes from elements. Okay. D1, D2, D3, D4. All right, so all I did in that step was I just performed the arithmetic and just kind of moved all the numbers down, just so it's a bit cleaner. Okay, and there's no boxes here to kind of muddle things up. Okay, but the boxes are useful. So when you're first starting out, I would definitely kind of box out each area so that you kind of know where to insert it. Because like I said earlier, one small mistake could actually make your solution quite far off. And so, I've seen it kind of all too often where you have this entry, and so maybe you write it accidentally in this spot right here. That's going to change the entire makeup of your entire solution. So definitely take it slow, take it meticulous, and don't feel bad about wasting paper. You want to make sure that you kind of do every single step. Otherwise, it's very easy to kind of make mistakes. Okay. All right, so now that we have our global linear system here, our next step is going to be to apply our boundary conditions. Okay. So boundary conditions is the last step that we need to do before we can actually solve this. We can solve this system here. Okay. So let's go back to our original figure and let's see what the boundary conditions are, and then mathematically apply that to our matrix here. Okay. Okay. So we have three boundary conditions that we need to account for here. And so on the one hand, we have node 1 that's attached to a fixed wall. So we can say that this is a fixed constraint. Okay. So remember, for a fixed constraint, we are going to apply a Dirichlet boundary condition. Okay. And then for nodes 3 and 4, we have forces being applied. So we have loads being applied. So node 3, we have a force. In particular, it's a tensile force. Any kind of force boundary condition will lead to a Neumann boundary condition. Okay. And then on node 4 there, we have a compressive force being applied. Okay. Which again is a force boundary condition, and so that's going to be a simple Neumann boundary condition. Okay. All right, so we have three boundary conditions to apply, and so that's three modifications to our global linear system that we have to do. Okay. Okay. So let's go through each of the boundary conditions. So first one is we have a fixed constraint on node 1. Okay. So remember, any kind of fixed constraint, a fixed constraint is directly going to specify the value of the solution at that location. Okay. Because node 1 is fixed to the wall, it is impossible for node 1 to move. So we can basically state from the beginning that D1 is equal to 0. Okay. So no displacement on node 1. Yeah.
For the boundary conditions, we have to remember these. So just thinking of whatever system we have, and we just remember it. Like, starting to remember this boundary condition and its value, and same thing for the other one.
Yep. Yeah, it's yeah, you basically have to yeah, you have to. I mean, for now, we're kind of writing through every single step, but then once you start doing kind of more of these, it becomes faster because you can kind of make note early on that this is a fixed boundary condition, and so that can kind of you can kind of write that in here already. But for now, I recommend kind of doing every single step just so you kind of see the whole process. But then as you kind of get better, then you can apply it kind of right away. So
Okay.
Yeah. Yes.
Why we haven't applied in the boundary condition of the node 2?
So node 2 has no external force being applied to, or no external effect. So remember, a boundary condition is basically any kind of external effect that's being applied to your system. So node 1 has an external effect because it's attached to an exterior wall. And then node 3 and 4 have external forces being applied. But node 2 doesn't have anything external that's being applied to it. It's basically just internal to the system. And so we don't have any boundary condition applied on node 2. If you want to be specific, technically there is a boundary condition on node 2. It's basically we're saying that there's zero force being applied. And so we have a Neumann boundary condition with zero force on node 2.
So net force is 0.
Exactly. Yeah. Okay. So to apply this Dirichlet boundary condition, basically remember the way that we apply this is that we replace the entire first row. Okay. So the first row in our global linear system is associated with D1. And so if we're going to be basically directly setting D1, we're going to eliminate that first row in our system. Okay. All right, because if you remember from last time, this simple equation here, D1 is equal to 0, we can kind of rewrite it in another form, right? And so we can say that D1 is equal to 0. Another way we can write this is 1 times D1 plus 0 times D2 plus 0 times D3 plus 0 times D4 is equal to 0. Okay. In other words, right, if we extract out the coefficients, we have 1, 0, 0, 0 multiplied by D1, D2, D3, D4. All that's equal to 0. Okay. Okay. And so if we apply this to our global linear system here, okay, we can say that we're going to apply this on the first row. Okay. Okay. We're essentially going to replace that with the equation that we just wrote out. So the coefficients in the matrix now become 1, 0, 0, 0. Okay. just like we kind of wrote down here. And then on the other side, this F1, in order to satisfy that equation, is we're going to set that equal to 0. Okay. All right, so that first row there basically represents the equation for our boundary condition. Because if you actually perform the multiplication where you multiply this row by this column, right, you end up with 0. Okay. Okay. All right, so that's the first boundary condition. Okay. Next boundary condition that we have is we have a tensile force being applied on node 3. And I believe the value for big F3 here is going to be 100 newtons. Okay. Okay, so if we go ahead and apply this, so applying Neumann boundary conditions is pretty simple because we actually don't even touch the matrix. And so the only thing that we do is we actually just apply that number directly into our forcing vector. And so basically what we're going to do is we're going to make a substitution where little f3 is going to be equal to basically just the value of that force, which is going to be 100 newtons. Okay. Okay. And so if we go back to our linear system here, let's go ahead and apply that. As we go to our third row, let me choose a different color. Okay. All right. So we have F3 there, and so we're just going to replace that with our value of big F3. And since it's a tensile force, we're going to apply a positive value. Okay. And so we're going to plug in 100 for that value. All right, and then we're going to do the exact same thing for node number 4. So node number 4, we have a compressive force being applied. And since it's a compressive force, we're going to apply a negative sign here, okay? So we're going to have F4 is equal to minus 50 newtons, okay? Okay, and we're going to do the exact same thing. So we know that F4 here is going to be on node 4. And so we're going to set F4 equal to minus 50 newtons in our linear system, okay? Okay, so if we go back to our linear system up here, let's go ahead and plug that in. So we have little F4 here. This is going to be minus 50. All right, and then last thing we're going to apply, and so kind of the last kind of F standing is node 2. So like I mentioned earlier, F2 technically is 0 because we don't have any external force. There's no constraint being applied there, and so we're just going to simply set F2 equal to 0. Okay. Since there's no external force or there's no constraint being applied there on node 2. All right, and so with that, we have our linear system here. And so this linear system here represents a set of 4 equations and 4 unknowns that we can solve for D1, D2, D3, and D4, okay? So technically speaking, we could probably solve this one by hand, especially since one of them we know already. We know that D1 is equal to 0. But I do want to show you how to actually solve this in MATLAB, just so you have it for your own, just for your own benefit, okay? Because, for future problems, we're going to look at systems that are, 8 by 8, 10 by 10, 12 by 12, 16 by 16. And so those situations, you just can't really solve it by hand. And so, knowing how to solve these in MATLAB is very useful. Okay. All right. Any questions on this, how we got to this point before we jump into, yes?
I kind of forgot a little bit of the last kind of lecture, but I'm kind of just wanted to ask you to jog my memory on like why we said so. Like I get that D1 it's 0. That makes sense. So that turns 0. Why did we do the 1 and then set all of them to 0 for the rest of it?
Yeah, that's a good question. So the question is, for the Dirichlet boundary condition, why do we modify the matrix to be this like 1, 0, 0, 0? So this row here is kind of a representation of our Dirichlet boundary condition, because essentially for a fixed wall, we're basically saying any node attached to that wall is going to be 0, right? So we have this equation here, d1 is equal to 0, right? And so what I'm saying is that, this equation here, we want to be able to implement this directly into the matrix. But, this matrix here not only accounts for D1, it accounts for D2, D3, D4, even though D2, D3, D4 are not present in this equation. And so the way that we do that is we kind of insert them in, but we just add a 0 in front. So we basically transform this equation, D1 is equal to 0, and we kind of expand it out to include all the other degrees of freedom as well, which is this one right here. So we have 1 times D1 plus 0 times D2 plus 0 times D3 plus 0 times D4, just so that we can insert that into the matrix. So those zeros become those other parts. Okay. All right, then we have a question from the chat. So a question from the chat says, if the Dirichlet boundary condition were on node 3, would it be 0, 0, 1, 0? Yes, it would, because, so this ordering of the nodes, so, we have to go chronological order, D1, D2, D3, D4. But if the Dirichlet boundary condition were on a different node, then we have to make sure we kind of activate the correct node. And so, if we have D3 is equal to 0, that kind of changes the coefficients here. So this would be 0 times D1 and then 1 times D3. So yeah, so the location of the 1 does matter. All right, any other questions before we move on to MATLAB? Yes. Okay. All right, so let's go ahead and launch MATLAB. And I should have done this before the class. It's not the first time I'll be forgetting to launch MATLAB.
Is this class kind of like if we can't show it in person, we can just do it on Zoom?
Yeah, so all the lectures you can attend on Zoom, no problem. The only days I require you to be here in person are going to be the exam days. Okay. Yeah, but every other day you can be on Zoom. No problem.
Is it recorded?
It's recorded, yes. Yeah. So if you go onto the Zoom or go into the Canvas site and you go to the weekly pages, there's links to YouTube which have the lecture recordings. Yeah.
Is that recorded?
Yep, these are recorded too. Yeah. Of course. Technical difficulties. Oops, not 80Y. I apologize, I should have done this before the class. I got 3 calls from during the lecture today. My friend keeps calling me. It's his name's Scam Likely. Always bother me during the lecture.
If you pick up a harassment next time, I'll call.
Oh, really? I had that happen before. So I lost my cat like 3 years ago, and I posted onto this this group, and I got a bunch of texts saying that someone found my cat, but I found out that they didn't find my cat. They're just trying to scam me. And so once I realized that, then I just kind of wasted their time, and then they called me some names I can't repeat right now because yeah. Okay. All right. We stalled long enough, so let's MATLAB is open. Okay, so let me go ahead and switch the screen share here. Okay. All right, so hopefully everyone wrote down the matrix that we need to solve, right? But essentially we have a 4x4 matrix that we need to solve for the solutions. Okay, so to solve this in MATLAB, I think let's make a new script. Okay. So basically we need to encode, or we basically need to define variables that have our 2 matrices here. So we have one, our forcing vector. Actually, let me do this just because I'm OCD. I have to start every script with clear all closed all CLC. Okay. Okay. So essentially, we need to define our vectors here that are going to be part of our linear system. So, if you remember, we basically have a matrix here. We have F1, F2, F3, F4. Okay. And then we have our matrix of values. These all come from the element stiffness matrices. And we have D1, D2, D3, D4. Okay. Okay, so basically we need a variable that's going to represent this vector right here. Okay. And we need a variable that's going to represent this matrix right here. Okay. So we're going to define those two things, and then we're going to use a special MATLAB operator that's going to solve our linear system for us. Okay. Okay, so let's start with our forcing vector. So just to keep things consistent, I'm going to call it F. Okay. Normally, I don't like to use variable names that are this short like this. We'll discuss this more when we actually get formally into MATLAB. But I think for now it's fine. Okay. So this F here is going to be a column vector. So it's going to have values that are going, from the top to the bottom. Okay. So if you go back to your notes, right, the forcing vector in our example here is 0 in the first row, 0 in the second row, 100 in the third row, and then minus 50 in the last row. So the way to do that is we're going to have 0 as our first entry. We're going to have a semicolon. So the semicolon basically tells MATLAB to go to the next row. Okay. Next row is going to be 0. Third row here is going to be 100. And then fourth row is going to be minus 50. Okay. So that right there, that is our forcing vector, okay, from our example. Okay. All right, next thing we need to have is our stiffness matrix. And so the traditional kind of variable for stiffness matrix is K, okay? And then just like we did with our forcing vector, we're going to build our matrix here row by row, okay? So, make sure you have your notes handy because I'm just going to go kind of quickly with the value. So our first row in this matrix is going to be 1, okay? So since this is a matrix and we're staying on the same row, we're going to separate each value with a comma, not a semicolon. So we're going to use a semicolon to go to the next row. Okay, so you have 1, 0, 0, 0. Okay. So that's the first row in the matrix. And then just to kind of make things a bit easier to see, I'm going to add those ellipses there, just so you can see I'm going to the next row. Okay. Next row is going to be, we have minus 500, comma, 850, comma, minus 100, comma, minus 250. Okay. Dot, dot, dot. Third row is going to be 0, minus 100, 100, and 0, semicolon, dot, dot, dot. And then last row is going to be 0, minus 250, 0, 250. Okay. All right, so I know I went a little fast there, but if you look at the values of this matrix, you'll see it matches up exactly with the example that we just did. Okay. All I did was I just built this kind of matrix row by row. So this here represents our global stiffness matrix. And I'll move the mouse in a second. Okay.
I'm curious, like on our tests, will we have to use MATLAB or is
No.
stuff done on paper?
No. So on the exams, I'm not going to expect you to solve the systems. And so on the exams, all you have to do is get up to the point where you apply the boundary condition. And then that matrix will be your answer. And I'll look at that answer. But yeah, obviously you're not going to have MATLAB on the exam. I know some calculators can solve linear systems, but it's also very tedious to kind of input all those numbers on the exam. And you only have a limited amount of time. So I have you guys stop right after the boundary conditions.
In the real world, like how important is it to be able to do this stuff in MATLAB? Because like, to be honest, my MATLAB is like trash.
Yeah. So in real world, for practical engineering problems, you're going to be using ANSYS. And so everything we're doing now, this is all part of just building up the theory. And so, practically speaking, you're not going to use MATLAB to do these kinds of problems, but it's the point of this part of the class is to kind of understand the theory so that, it kind of fills in the gaps. Because, if you just use ANSYS, there are things that happen that you don't really understand what's happening. But, doing this, you kind of understand. All right, and so now that we have our vectors and matrices defined, that's all the hard part. And so the last part that's easy is to actually do the solution, right? And so our solution is going to be D, okay? And so to solve for D, we're going to use a special operator in MATLAB called the backslash operator. And so, most people are familiar with the forward slash. So the forward slash, this is used for division. But the backslash is a very special operator in MATLAB that basically says that, we have this linear system that's defined by this matrix and this vector, and we want to solve for the solution to that linear system, okay? We're going to do K, which is our stiffness matrix, backslash F, which is our forcing vector, okay? And that's it. And so we basically are going to run. Okay. And then this D vector here has the solution to our problem here, okay? And so this D vector here, our first value here is D1. Okay. I apologize. The mouse in this room is very finicky. So it's always going to look like I have serial killer writing, but that's just the best I could do with the mouse. And so, all right. So first entry D1, you can see is 0, and that matches up because remember D1 was the node that's attached directly to the wall. And so it makes sense that that value is 0 because that was our fixed constraint. Okay. D2 is the second entry. So that our D2 in here is 0.1 meters. And so you can see that our node 2 does not really change in position all that much, which makes sense because if you think back to the problem, we have kind of opposing forces. We have one force that's pointing to the right, another force that's pushing it to the left. And so it kind of makes sense that those two kind of cancel out and we don't really have that much deformation there, okay? Node 3 is where we see the biggest deformation. So that is a 1.1 meter deformation for node 3, okay? So if you think back to the problem, that also makes sense because node 3 is directly where the force is being applied. And so that was a force of 100 newtons in the tensile direction, okay? And the element that it's connected to, element B, also had the weakest spring constant. And so, it doesn't have that much resistance to resist that motion. And so it makes sense that that value is the highest, okay? And then finally, we have D4, which is the deformation of the last node, node 4. And you can see it is also very small, but also in the negative direction, because that's where we had our compressive force, okay? Let me just check with the notes. That is exactly our answer. So this is what we get, okay? All right. So we're technically not at the MATLAB portion of the class just yet. And so, this part of the class, this is just to help you solve these linear systems. The MATLAB is definitely going to get a lot more intense later on once we actually start developing our MATLAB code. But at that time, we'll do kind of a more extensive MATLAB review. But for now, I just wanted to kind of review or just kind of go over with you guys how to solve a linear system, just so that you can actually do these for your hand calculations, okay? So, because I'm not expecting you to solve these, 4x4, 5x5, 6x6 linear systems by hand. And so use a calculator, use MATLAB. It's going to be a lot faster for you guys.
Question.
Yes.
Is there any difference between doing that line 11 versus using the Linsolf function?
Yeah. So the Linsolf function gives you more custom. There's more custom options with Linsolf. So the backslash basically just uses the default. Backslash is the same thing as Linsolf, but it uses the default settings for it.
Oh.
And so if you use Linsolf, you can actually change, what technique you use, what tolerance you use for the linear system. For simple problems like this, it's probably not going to make a difference. But for more bigger systems, then you might want to have more custom settings. Then Linsolf might be more useful.
Okay.
But for everything we're going to do, at least in terms of hand calculations, the backslash is perfectly fine for that. Yeah, good question. All right, any other questions about this? Okay, all right. So that's the whole finite element process. So that kind of took a bit longer than I expected, but I think that's pretty typical. I always say that every time I teach this class. Okay. So for the last 15 minutes, let's go ahead and introduce the concept of a truss element, and then we'll pick it up again on Thursday. Okay. Okay. So that last example that we just did was a good illustration of the finite element process. And so, like I mentioned kind of earlier today, that, no matter what type of technique or no matter what implementation of the finite element analysis that you're going to be implementing, you're still going to be following the same 4 steps. And so you're going to be computing element stiffness matrices, you're going to be assembling the global linear system, you're going to be applying boundary conditions, and you're going to solve in some way or another. Okay. The only difference that occurs is basically going to be in the types of elements that you apply. Okay. And so, so far we've gone over one type of element, which is spring elements, right? Springs are kind of the simplest thing you can do. And so a truss element is basically just another type of structural element that we can apply. Okay. Okay. But again, the same process is going to apply. And so I guarantee you guys are going to be very tired of this process, but that is kind of is what it is. Okay. So what is a truss element? And so a truss element, you may be familiar, that might kind of ring some bells, especially, if your undergraduate wasn't too far away. A truss element is a particular type of structural element that's designed to handle loads in tension and compression. Okay. Okay. In fact, I think, when you first learn about structural design, one of the principles that, generally you want to design your structure in a way that, most elements behave as trusses. And so, generally most materials are strongest in tension or compression, or tension and compression. And so if you can design your structure in a way such that every element is loaded in tension or compression, that's usually going to lead to a much more stable, much more safe design. Okay. So for example, right, I think the most striking example of truss elements that you kind of see out in the wild is basically any structure that's designed with thin elements. And so if you look at kind of the supporting structures for our electrical wires, okay, or our phone cables, right? And so a lot of cities, it's becoming more popular nowadays to kind of bury the electrical wires underground. But a lot of cities still have electrical wires that are suspended kind of in the air, so they're kind of away from people. Okay.
Telephone poles?
Wait a second.
Telephone poles?
Telephone poles. Yes, that's the word I was looking for. But you'll have structures that kind of look like the following. So at the top, you may have, this is where the telephone wire or the electric wire is suspended, right? You have kind of all these kind of thin kind of structural elements that kind of make up the structure from there. Okay. Okay. It's a very poor drawing of one. I'm going just based off my memory of what these look like. Okay. Okay. So every single one of these is a truss element. Okay. Right. So primarily, this structure, for the most part, the structure here just kind of has to support its own weight. And so most of the loads are kind of going vertically downwards, okay? And so this structure is designed in a way where every single element here is really only supporting just its weight in tension or compression, primarily compression, okay? Okay, so trusses are a very common, structural element. And so, it makes sense that we're kind of moving on to discussing these things. Okay. Okay, so let's go ahead and draw one out. Okay. And let's start the derivation for the element stiffness matrix for a truss element. Okay. All right, so if we draw a single truss element, so a truss element is basically like a rod. Okay. So this rod here is going to have a particular length. Okay. It's also going to have a particular cross-sectional area, okay, which we're going to assume is uniform. So we're going to assume that the element has the same cross-sectional area throughout. Okay, so we'll call that A. And another thing that we'll define is that, we'll assume that we know the material for our truss element too. And so we're going to know the Young's modulus for the element as well. Okay. So those are the properties of our truss element. Okay. All right. So now that we know the geometry and we know the materials of our truss element, we need an equation that's going to represent kind of the relationship between forcing and response for our truss element. Okay. And so the equation that we have for this is actually it's actually another it's kind of a generalization of Hooke's law, but for a general material, not for spring. Okay. And so the stress strain relationship for a truss element is given by the following. So we have sigma here being the stress in the truss is equal to E, the Young's modulus, multiplied by epsilon, which is the strain. All right, because what's going to happen is that if you apply a force to this truss element, so let's say that we apply a tensile force, okay. Right, so we apply a tensile force, one to each side, okay. We apply the same force on both sides, just like we did with the spring, just so that we can assume that this truss element is in static equilibrium, okay. So what we expect to happen in this case is that the truss is going to elongate, okay. Okay. All right, so let's go ahead and quantify that, and let's put it in a form just like we did with the spring, where we can basically make a system of linear equations that describes this behavior, okay? Okay, so let me go ahead and draw out the truss element again, okay? Just like we did with the spring, we're going to label each side of the truss, and so we're going to label the left-hand side node 1, right-hand side is going to be node 2, okay? All right, we have our tensile force. T, T, okay? Right? And then as a result of applying these forces, we're going to have displacements as well, okay? Now, just to keep things consistent, I'm going to define the positive direction for the displacement to be going to the right, right? And so I know that, you apply this tensile force, node 1 is going to move to the left, but just the way that we're going to define the direction for the displacement, we're going to define it going to the right, okay? So this is going to be D1. And on the right-hand side, we have D2. Okay. All right, so let's take our definition for the stress strain relationship in a truss element, and let's relate it to the variables that we have down here below. Okay. So in other words, we want to rewrite the stress and we want to rewrite the strain in terms of the quantities that we have on our element here. Because once we do that, we'll have our equations that we need to get our element stiffness matrix. Okay. Okay. All right. So let's start with a simple one. So let's start with stress, right? And so if you think back to your structural mechanics course, right? Stress is nothing more than just a force that's distributed over an area. Okay. So we actually have both of those things, and so we have a force, right? So stress is equal to force divided by area. Okay. So we have our force, right? So the force in this case is going to be our tensile force T. Okay. And we have our area as well, because one of the properties that we know about our truss is that we do know its cross-sectional area, right? And we know that that cross-sectional area is going to be uniform throughout the entire truss element. Okay. And so we can redefine the stress as simply as T divided by A. All right. Next, we have the strain. Okay, so the strain for at least for a linear bar like this, which is only deforming in one direction, is just going to be the change in length of the bar divided by its original length. So the original length of the truss element, we have that already. That was one of the properties that we started with. So remember, we defined that original length as just simply L. Okay. And then the change in length, we can define that in terms of our nodal displacements, right? So we know the displacement of the second node is going to be D2, and the displacement of the left node is going to be D1. Okay. So the change in length, or how much this rod is going to change length, is going to be nothing more than just D2 minus D1. Okay. So if we just subtract those nodal displacements, that'll give us, how much the bar is going to go. Okay, so let's go ahead and plug those in. So let's know that we have different expressions for the stress and strain. Let's go ahead and plug that into our stress-strain relationship up here. Okay. So we plug that in, we get sigma is equal to E times epsilon. Okay. And you plug that in, we get T over A is equal to E times D2 minus D1 divided by L. Okay. So let's do a little simplification. So let's isolate the T on the left-hand side by itself. So I'm going to multiply both sides by A. Okay. And so we get T is equal to AE over L multiplied by D2 minus D1. Okay. So unfortunately, we are out of time, and so I am going to stop here. But before we take off, I do want to point something out, right? And so I want to relate this back to our expression for springs, right? So if we think back to springs, right, and we think back to not just the Hooke's law, but the generalized Hooke's law that we had, right? So generalized Hooke's law, we had T is equal to K times D2 minus D1, okay? Basically a relationship between the force that we apply on the spring and its nodal displacements, okay? We can see that for our truss, we get a very, very similar expression. The only difference is that, instead of a spring constant, we have this combination of terms here. So we have A times which is the cross-sectional area, multiplied by the Young's modulus, divided by the length, okay? And so what we can see here is that, this combination of properties, this becomes kind of like the effective spring constant for the truss. And so knowing that our equation here has a similar structure to the spring means that, our truss should behave very similarly to springs. And in fact, they actually do. Okay. The only difference is that the way that you compute that spring constant is just different for truss. Okay. All right. Any final questions before we wrap it up for today? Okay. All right. So that's all we got time for today. And so when we come back on Thursday, we'll finish this derivation of the truss element stiffness matrix. We'll do some more examples, and then we'll move on to 2D problems from there. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Yep.
I wanted to ask, you had a prerequisite for another class, I think that's for some ones on that. How important would you say would be to have taken?
So the prerequisite for this one is 410. So I basically am teaching it assuming that you have not taken 410. And so 410 definitely helps because all the stuff we're going over right now is 410 stuff. But I know that grad students, you guys are coming in with all different backgrounds, and so you probably didn't get the chance to take 410.
Yeah, exactly.
And so I'm teaching everything kind of from scratch. The only difference is that I am going pretty fast with this stuff. So just kind of make sure that you're kind of keeping up the first few weeks, and then you should.
Thank you so much.
I told you that I had to do that one problem twice.
Yeah.
So just going over what I had done over the weekend, and then looking at you going over the problem. What I noticed is that there was a relationship that the diagonal always had the most, not the. Is that typically the case?
It is. That is a great observation. So the diagonal terms are, if you look in terms of where they are in the matrix, it's always the double. So it's like node 1, node 1, node 2, node 2.
Yeah.
And so those are always where the positive numbers kind of converge. And so you're always going to have the highest numbers on those diagonal. In fact, that's a sign of a healthy matrix. Because if you have kind of the highest numbers outside of that, that leads to some really kind of wonky stuff.
Yeah.
So, yeah, that is true, and that is definitely intentional to have the highest numbers.
Oh, yeah, because when I did it the second time and I was comparing what did I do wrong, I noticed that because I didn't quite make that observation yet, everything was just all over the place and I added stuff wrong. And
yeah, okay, that's why it's really important to be organized. Because one small thing and things that you
right.
Set the whole.
Okay, so I guess that's and I kind of have a strategy in terms of organizational wise, how to because what I'm thinking is come exam time, well obviously we're time limited, so it's like yeah.
Okay, for sure. The exams are very challenging. Not because the content is challenging, it's just that there's a lot to it.
Yeah.
And so every time I give an exam at FBA, like students go after us. There's just a lot of numbers. Yeah, and you want to be organized. You don't want to be going back and erasing things. That's
Told you,
time
I
and
know how to
donation
do
rate.
this stuff.
Yeah,
So,
because what I
like,
realized
I
too
shouldn't even
is that
study, okay?
the number of how big your node will be dependent on well how many elements touch that particular
Exactly.
node.
That's a great observation. We're gonna go through that more again too, because it's that situation is pretty dry. Usually you don't have a 1D system that looks that, but in 2D systems you could have 3-4 elements converging on the same point.
Yeah.
And so in those situations you're gonna have a lot of concentration of those.
So how would you do an analysis on because obviously in the real world the springs are going to deflect both in your X and Y. So how would you go about that?
Yeah, so well, in those situations, you would probably use a different type to define it. So, we're covering basically just compression and trusses are kind of the same. Beams, we're gonna start to look at the perpendicular, the transverse deflection.
That's always so.
But the most general element of frame elements, which can be compressed and intense and do up and down. You'll see when we get there why that's not practical to do by hand, because, for these problems, the element stiffness is just 2x2.
Yeah.
But for frames, in the most general sense, the element stiffness matrix is actually 6x6.
Oh,
Okay, so instead of getting 4 values, you're getting 36. And then you're assembling that into a matrix. So that's definitely the whole point of the class. You're all gonna hate it.
What's it called? So at work, I was looking into compliant mechanisms.
Yeah.
How would you go without deflections? I was trying to see look at computers as to how they would go deflection and compute that into a force. But then I looked at it and I'm like, oh, it went past me. So how is that something we would want to do?
That one probably, it's compliant. So usually for those cases, we have large deformations. And so for those cases, we have to pump. You can't really do that. You're gonna have to basically rely on the software. It's trust that it's implemented. And then model it. And you get to the magic.
Okay. All right.
Yeah, sounds like a beefed-up version. Hey, Brian, what's up?
Just had a question.
Yeah.
The typically the class taken, is it like a derivative equals 0?
Yeah.
And right here is like a force.
Yeah.
So I was like thinking how does it relate?
Yeah, so Neumann's actually a
It's
general.
up to you, man. You're running out of time though, Friday.
So basically any boundary condition that's on the so here we kind of jump a few steps. So the force, technically you can relate to a stress on the structure. And a stress is essentially derivative
This is the
of
apartment.
this weight related by a stress strain relationship. So we kind of jump to it.
Oh, like as equals and make
Exactly, but in a technical sense, Neumann boundary condition is derivative equal. Most commonly, you'll have like a stress-free boundary condition, which is derivative equal to 0.
Yeah.
But you can set that derivative equal to whatever.
That does not
essentially
apply.
what we're doing.
And D2, D1 split, you said it's going in the towards the right,
Yeah.
and
It's just one lecture, not
right here in the equation you put D1 minus D2 minus D1.
Yeah.
If the tensile force pushes the rod in the left direction, is that a negative D1?
Exactly, that's why we have minus there. We define the positive direction to go to the right, but we know it's gonna go to the left. That's why we have that as minus.
So it's already attributed in the
Exactly.
equation. It's not a D2 minus.
No, yeah, so
Okay.
we've already kind of already accounted for it.
Well, thank you, Dr.
Yeah, no problem.
Okay, so I did want to ask, so I know that the pumps are working out at school, whatever.
Yeah.
I just want to make sure that when I get the course, it counts as an elective and
It
not
does.
like a grad type thing.
No, it'll count as an elective. We're gonna have to go in and do what's called the TEA exception, but I'll go ahead and do that.
Okay, appreciate it.
Yeah. How's it going?
3:22. That class like queued up outside the door.
Oh my God, all 50